So our next speaker is Jane Yu from the University of Victoria in Canada, and she will tell us about second-order optimality conditions for non-convex programs. The floor is yours, Jane.
Okay, so thank you for your invitation to join the meeting from Canada. So this is a joint work with Helmut Freire from Austria and Jinchuan Zhou from China. Okay, so first I'm going to review the second order optimality conditions. Then I'll talk about our new second order optimality conditions. Okay, so we will study set constraint optimization problems. Okay, so here all the functions are C2 and the omega, the set is just assumed to be a closed subset. In particular, omega can be non-convex. So if omega is this set, then this is just reduced to the standard nonlinear programming. Or if omega is a convex cone, okay, then this is cone constraint. It's just like second order cone, right? Programming or semi-definite cone programming. If omega is a disjoint set, which means it's the union of finitely many convex polyhedral convex sets, then this is the disjunctive program. If omega is the complementarity set, then it is a mathematical program with equilibrium constraints, or so-called MPEG. So this problem setting is very general. Okay, so first let's review the second order optimality condition for the nonlinear programming. So this is the linearization cone, right? So it's just linear approximation of the tangent cone. Then the critical cone is the intersection of the linearization cone with this. Okay, so this is like directional director F at X bar in direction D should be less equal 0. And this is the Lagrangian function and the multiplier set. So under certain constraint qualification, I think such as MFCQ, then we know that there must exist a multiplier. So that's KKT condition. And for each direction, each critical direction, there exists a multiplier such that the second order condition holds. Okay. Okay, so let's review the classical results for the case where omega is convex. So there are a lot of all these results you can find from Bonos and Chapinot's book, Perturbation Analysis of Optimization Problems. So for these kind of problems, the multiplier must belong to the normal cone of omega. And this is the first order condition, right? KKT condition. Okay, to describe the second order optimality condition, when the boundary of this set may have some curvature, right? It's not flat anymore. Then one need to use the second order tangent cone. Okay, so these are the definitions. So for tangent cones, we have two kinds, right? The first kind with the head is the so-called regular or Clark tangent cone. And then this one without head is the tangent or the so-called contingent cone. And the second order cone or the so-called outer second order tangent cone is defined by this for each D which is in the tangent cone. Okay, even when this set is convex, the second order tangent comb may be empty or maybe non-convex. So this is very different from the first order tangent comb. Okay, so recall that the constraint, okay, is this, right? When omega is convex, then the linearization cone will be this, right? It's approximation of the tangent cone. So here, the tangent cone to omega, and then the critical cone is defined by this. Okay, so for the convex, I think convex set constraint program. So this, if the Robinson's constraint qualification holds, then for each direction, each critical direction, and any convex set on any convex subset of the second order tangent cone, you can find a multiplier such that this second order condition holds. And the difference with the nonlinear programming case is that it's possible to have this sigma, which is the support function on the right-hand side. Okay, so this is all in Bonner and Xiaopin's book. So the sigma term describes the curvature of the set omega. If omega is a polyhedral convex set, then this term vanishes. If the second order cone is convex, then one can just replace it by the second order tangent cone. Right? But as we said, even if omega is convex, you cannot guarantee the tangent cone, second order tangent cone is convex. And then in that case, you have to find a convex set, convex subset to have any result like this. Okay, so this is a classical result. So the questions we want to ask is how to generalize the second order optimality condition to the case where omega is not convex. The question is, can we still use the support function in the condition? Okay, so first, we can look at the support function. This is the definition of support function. Suppose in the very nice case where S is convex and the support function is achieved at certain U bar, then by optimality condition, we have this. It's just simply the optimality condition. And then, so it means that if S is convex and the maxima is achieved, then sigma support function at lambda equals lambda transpose U, if only if lambda is in the normal cone at U. Okay, so this will motivate us to introduce a concept for the case when S is not necessarily convex. So recall that when S is convex, we have this, right? So for any given set, we define the lower generalized support function to S as the mapping. Okay, so here we take so this is a definition. Well, support function can be defined for any set, but the question is whether they can be used for non-convex in the second order condition when set is non-convex. Okay, so we introduce, so then this here, because S is not necessarily convex, so this normal cone, by this we mean it is the limiting normal cone. Okay, so then we prove this relationship between the standard support function and the lower generalized support function. So you see this, you got a lot of infima here, right? So first infima over U, then the lim inf. So this got to be less or equal. So, and when S is convex, then it's equal. Okay. So this is in general, the sigma hat is in general smaller than the support function. So, okay, so in our second order optimality conditions, okay, we are trying to use the sigma hat. So then it's a smaller one and it's easier to hold. And even the constraint qualification we are going to use is weaker than the usual one. And the first order optimality conditions are stronger than sharper than the usual one. So to achieve this, we need to now define the directional constraint qualification and directional first order optimality condition. Okay, so suppose we have a direction, just like a direction in a critical cone, right? In a critical cone. So suppose this D is the given direction in a given direction. Then the directional neighborhood is no longer this unit ball, open ball. It is a unit open ball and intersect by this fan. So it is a section, and the section is divided by this given delta. Okay, so and around the direction D. Okay, so we'll use this neighborhood. So this neighborhood, if the direction is equal to 0, this direction neighborhood is just the standard neighborhood. But if the direction is non-zero, in general, this directional neighborhood will be smaller. And the smaller is the delta, the smaller is the direction neighborhood. Okay, so then there is the matrix of irregularity in direction. So, so we look at the set value map, right? Because we are our constraint is gx in omega. So you can construct a set value map. And we said this set value map is matrixly subregular at the point in the graph in direction D, if this error bound condition holds. Okay, so here the difference is that now this neighborhood, the standard neighborhood, is replaced by directional neighborhood in direction D. So if the D is equal to 0 in this definition, then it reduced to the standard matrix subregularity condition. Okay, so now the limiting normal cone is extended to directional normal cone. So here, just assume that, okay, so this notation, so xk approach converges to x bar in direction D, means there exists some tk converges to 0, dk converges to D such that xk equals x bar plus tk dk. Okay, so in the limiting normal cone direction, if you change the standard sequence convergence to the convergence in direction, then you can define the limiting normal cone, and also you can take the closure convex hole, then you get the Clark normal cone in direction D. So when D is equal to 0, then directional limiting normal cone is just the standard limiting normal cone. And the directional Clark normal cone is just the standard Clark normal cone. So the directional normal cone is in general smaller than the non-directional one. Okay, so now we need some sufficient condition for matrix subregularity. So this is the directional first order, so-called directional first order sufficient condition for matrix subregularity. So this, suppose X bar is feasible, right? So this is like our feasible point of our constraint. And D is in the linearization cone, okay? And then this is the condition, right? And this is, if you remember, the so-called Mordkovitch's criteria. This is different with the Mordkovitch criteria only in that here we take the direction. If the direction equals 0, then this is the Mordkovitch's criteria, which is equivalent to the matrix regularity. Okay, but if this directional, the smaller limiting direction limiting normal cone is used, then it is a weaker one. Okay, so we will derive the right result under this weaker condition. So, and then there's also a sufficient condition called directional quasi-novelty, which adds a sequential condition on this condition. So it is even weaker. Okay, so this is a relationship. So here, okay, so the first one is sort of like a directional MFCQ. And then it must be stronger than quasi-novelty in direction D. And the quasi-novelty implies matrix subregularity in direction D. So, the matrix subregularity in direction D will be enough for us to derive optimality conditions. Okay, so I already said it's all these constraint qualifications are weaker than the Mordkovitch criteria, or so-called, or we can call it non-smooth MFCQ. In particular, they are weaker than the Robinson's constraint qualification. For example, if G is alpha and omega is the disjunctive set, then the directional quasi-novelty holds. Okay, so first we can, okay, so as I say, we not only can derive second order condition, our first order condition is also sharper than the usual one. So we will use the directional first order optimality condition. So here you can see that the difference is now that you replace the normal cone, right, the limiting normal cone, by the directional limiting normal cone, which is smaller. So the multiplier is in a smaller set if D is non-zero. Okay, so this is the first order condition, right? And it holds under the matrix of regularity. Okay, so in directional KKT condition is sharper, in general, sharper than the KKT condition, unless D is equal to 0. Then you recover the standard one. Okay, and what about second order necessary optimality condition? So here we just assume the matrix of regularity constraint qualification holds at X bar in direction D, a critical direction. So this part, and then assume the second order tangent cone is non-empty, then there exists a directional multiplier such that this holds. So the difference between this and the result, the classical result, is that now we use the lower, the sigma hat, right? The lower generalized support function. Okay, and now we can, so now the first common is even the first order condition is stronger, okay, and it's a directional type. And this go with the second order, because to the second order condition always says that given a critical direction, you have the second order condition, right? So now given this direction, right, you can have the multiplier in this direction. Okay, so this is different from the nonlinear programming, right? It is because you have a set which is even non-convex. So when in the case when this omega and the second order tangent cone are both convex, then this second order condition is same as the classical one in Barnard-Sharpnell's book, but the constraint qualification required is weaker because in the book, the Robinson CQ was required. Okay, so now we have, okay, so now in the result, we have, in this result, we assume very weak constraint qualification. And what we can get is this second order condition with the sigma hat. Okay, can we get a result with sigma, the support function? If we want to remember, sigma is bigger in general, right? Bigger than the sigma hat. So if we want to get the result with this replaced by sigma, we probably need some stronger condition. Okay, so this conditions we call directional Robinson's constraint qualification. So here, if you remember the Kovic's criteria or the first order sufficient condition for metric subregularity, here is you use the limiting cone. And if you use the Clark cone, then it will be bigger, right? So this will be, if lambda is in this bigger set and it still implies lambda equals 0, then this condition must be stronger because it's a bigger set, right? So it is stronger than first order sufficient condition for metric subregularity. Now, if we have this stronger condition, then we have this, okay, so then the first order condition will say that we will have multiplier, which is in a directional Clark, is a directional Clark multiplier set. And then this we can use sigma instead of sigma hat. Okay, so the constraint qualification use is stronger, and but the second condition is sharper because sigma is greater equal to sigma hat, right? If this holds with sigma, then because it's greater equal to sigma hat, it will also hold with sigma hat. Okay, so when omega is convex, then this condition is equivalent to Robinson constraint qualification. And the directional multiplier is the non-directional multiplier. And the theorem recover a classical theorem in Barnard-Sharpnell's book. Okay, and there are more directional multiplier sets, right? Because you can define, you can use, okay, this one we already use, Clark directional normal cone. And what about regular normal cone? We do not have, we can use, we do not use define regular in direction D, but you can say that this you can use a regular normal cone to the tangent cone. So this will also define strong multiplier. When D equals 0, all this concept recover the strong Mordkovich Clark stationary condition. Okay, so now we have some more conditions. Here we assume this non-degeneracy condition. So here, this is the span of the limiting normal cone. Okay, if this condition holds, then all the multiplier sets coincide and it's unique. And we have this second order condition in terms of sigma. Okay, so the result extends a classical result in the book to allow a non-convex set omega. Okay, so now we also can extend, can have some sufficient optimality condition. So here we will need the second order condition in the strict inequality form and using sigma. So, right? Under this condition, the second order growth condition holds. Okay, so now we have two kinds of second order conditions, right? Sigma or sigma hat. Okay, we call this relationship, sigma hat is in general smaller, and they are equal when the set is convex. Okay, so we have this, right? If you have a condition in terms of sigma, of course, the condition with the sigma hat will hold. Okay, so the second condition in terms of sigma is stronger, and the one in terms of sigma hat is weaker. So there is an interesting observation here. It doesn't happen when you talk about nonlinear programming or convex set constraint. For nonlinear programming, you don't need sigma, so there's no difference. And for the convex set constraint, they are the same. So you have the same, you always use a sigma. But for the non-convex one, sometimes you need to use sigma hat because it will hold under weaker condition. That's what I observed. So yeah, this is the reference. And I think that's all for my talk.
Thank you very much, Jane. Do we have any questions for Jane?
Can I ask a question?
Yeah, please, Bruno.
Yeah.
First, thank you very much for the talk. I'm just curious about one thing. So originally you have a constraint on the form Gx belongs to omega, right?
Yes.
And then you consider the possibility of omega not being convex. So what happens? Yeah. So suppose originally that omega is convex, and you define a new omega that is just a set of x such that Gx belongs to the original omega. So
can you say again? You have an omega which is convex?
Convex, but then you define a new omega, which are the x that belongs such that Gx belongs to the old omega. So
no, I didn't. I just consider the constraint Gx is in omega.
I'm just going to ask what happens if you try to see the convex case, put everything inside omega. So suppose omega originally is convex, and then you define a new omega that contains the constraints, and try to analyze using the tools you developed whether you would get something similar to what Bollens and Shapiro originally obtained. Sorry, perhaps I wasn't able to explain well,
I'm
but
confused.
the formulation of the problem.
With the new omega that you talk about, then you also have a new function G, which is just like the identity. Is that correct, Bruno? Or
no, my problem is just G is in omega, right?
Yeah. So can you show the problem again?
Yeah, it is. So my problem is.
Yeah. Yes. So
it's this.
So what I'm saying is that you have Gx belongs to omega.
Yeah.
So you write this as x belongs to omega bar.
X belong to omega. Yeah, okay. Omega bar.
Yes.
But the omega bar is not. Yeah, so you mean the omega bar means the constraint Gx is in omega, right?
Yes, and then so you treat this as the omega in your theory.
Yeah, but what's this new omega head cannot be convex, right?
Yes,
Or
yes,
you-
exactly. But your tools can analyze this even though it's non-convex, right? So I'm
right.
asked, yeah. So my question is, what is the relationship between these two things? So you have a new.
So it's like you if you define implicitly, so then you will need some kind of chain rule or something, right? Because you get some function inside of your new set. You can use some yeah, whatever you do, it's not implicit in terms of problem functions, right? You like to describe in terms of G, right? So if you are hiding it like using an implicit set, you will have some, say, maybe tangent cone, right? Yeah, there will be some tangent cone, and in our paper you can see you can describe the tangent cone, right?
Oh.
Yeah, there is a relationship between the tangent cone of the set you create, the first order and the second order, right? So it's like, for example, tangent cone, you can write the tangent cone. If under constraint collocation, you can write tangent cone in this, not this, I mean, yeah, like this, right? So if you have a big set, a big omega bar, then there will be connection of the tangent cone with this. This is like a linearization of the tangent cone of the set you describe, right? And also you can have the second order type, right? You can take the second order tangent cone of the set you create, and then you can relate it to the Hessian matrix of G and the second order tangent cone of T, of the omega, okay? And we would like to describe the condition by the function G and the tangent cone or the second order tangent cone of omega, right? We don't like to have it all in one piece, right? Implicit, right? So that's maybe the difference.
Okay, sorry, I think I used a lot of time. So I was just wondering what would. Okay, I understand. Perhaps I'll ask more details later. Thank you very much. Thank you.
Yeah, I think we should get on to the next speaker. So maybe you can continue the discussion offline. So thanks again,